This is chapter 4, section 6, the mean value theorem. This section looks pretty easy, but when you start getting into details, it gets a little trickier. And people have trouble on this, not at the basic problem, but the applications of these. So make sure you are following and understanding everything I'm talking about. So we're going to start with Rolle's theorem, which you really technically don't have to know because the mean value theorem will cover the Rolle's theorem within it. But in the progression, you have to prove Rolle's theorem first, and then that is used to prove mean value theorem. That's why it's listed first. So certain conditions, continuous on a closed interval from A to B. That is the first requirement, must be true. Second thing must be true, differentiable on the open interval from A to B. If you don't know the difference between a closed interval and open interval, you should find out. That's important. And the third condition, f of A equals f of B. If those things are true, then what's the conclusion? There exists at least one point C. So that implies there could be more than one, but you're guaranteed at least one. That point C is in the open interval A to B. So it's between A to B, not including A and B. And at that point C, something special happens. The derivative is equal to 0, or the slope of the tangent line is 0. So I'm going to look at the example to the right at first. So first, is this function continuous? Well, this is a polynomial, and we know polynomials are continuous everywhere, so it meets the first condition. I'll label these 1, 2, 3. Second condition, it must be differentiable, and we know polynomials are differentiable everywhere, so it is differentiable between 0 and 4. The third condition, f of A and f of B. Well, that's my A and that's my B. So I need to find f of 0 and f of 4. And f of 0 is negative 4. And f of 4, that's going to be negative 16 plus 16. Those will cancel. I'm going to get negative 4. So the third condition is met. The endpoints have equal values. If that's true, they're saying there's got to be one point, at least one point, where the derivative is 0. Now, if you look, it's pretty obvious where the derivative is 0. It's right there. Because if we draw a tangent line, that's the point where the slope is 0. And just to make some connections for you, that is my C. C is 2. So what is this saying? There's going to exist at least one point C in between A and B. So between 0 and 4, there's going to be one point, which we call C, is right here, where the slope of the tangent line is 0. So why is that obvious? Well, if you start drawing tangent lines, eventually you got to get a 0 point, right? In this. So that's what it's saying. So let's apply this to the one on the left. So, continuous. Well, all polynomials are continuous. 1 is done. Differentiable. Polynomials are differentiable everywhere. That's done. Third, f of A must equal f of B. So I need to find f at the left endpoint and f at the right endpoint. Plug in 0, I'm going to get 0. Plug in 5, that's 125. And then 25 times 7, that's 175. So 125 minus 175 is negative 50. Negative 50, and then that's 50, so that's 0. So condition 3 met. The endpoints are equal. So the conclusion is there's got to be at least one point where the slope of the tangent line is 0. In this case, there's actually 2. One right there, And we have another one right there. So that's why it says at least one. You're guaranteed one. You could have more than one. In fact, you could have infinitely many points where that happens, depending on the graph. So that's why it says there exists at least one, meaning there could be more than one. So I claim there are two C's. The first C, I'll call C1 right there, and the second C is right there. So C's, what are your C's? They're values of x between the endpoints. Well, the endpoints are 0 and 5, so there's my first C. So at that value of x, the derivative is 0, and there's my second C, because at that value of x, the derivative is 0. So that's the application of mean value theorem. That's all it's saying. So remember, important, 3 conditions: continuous on a closed interval, differentiable on the open interval, and the endpoints are equal. If all those 3 are true, there's got to be at least one point where the slope of the tangent line is 0. Could be more, as in this case. So that is Rolle's theorem. It's used quite often in FRQs, and you see them in multiple choice problems also. But now, why conditions 1 and 2? Why continuous? I will show you. If you have a function that's not continuous, see that? Now my endpoints are equal. F of A and F of B both equal 0. But if you look, there is no place where the tangent line has a slope of 0. So continuity is a must in order to guarantee that. Okay? The second condition says it must be differentiable on the interval. Well, I have an example where it's not differentiable. There's a sharp point, and we know the derivative does not exist there. It's continuous everywhere, but not differentiable. So therefore, let's take a look. F of A and F of B, man, those are equal. They have the same y value. So that looks like it meets the conditions of Rolle's theorem. But the one condition it doesn't mean is not differentiable. And if you look, there is no place where the derivative is 0. So therefore, those are examples of why you must have continuity and differentiability. If you don't, the Rolle's theorem is not guaranteed. Okay, so we're going to do a problem here. This is an example. Determine whether Rolle's theorem applies. So conditions 1, 2, and 3 must be met. Condition 1, is it continuous? I'm going to say it is continuous. I'm going to write properly. F is continuous on 0 to pi over 2. How do I know that? Because in chapter 2, we learned the sine function is a continuous function. So step 2, I'm going to claim f is differentiable on 0 to pi over 2. So we learned that the sine function is differentiable everywhere. There are no sharp points. There are no discontinuities. So our first 2 things are met. Step 3, we need to show what f of 0 and f of pi over 2. We have to show that the endpoints have the same y value. So f of 0, the sine of 0 is 0. F at pi over 2, well, pi over 2 times 2 is pi, and the sine of pi is 0. So I've shown the first 3 conditions are met. It's continuous, it's differentiable, and the endpoints have equal y value. So therefore, the guarantee, the result is there must be at least one point where the derivative equals 0. And we call that point C, so I'm going to call it f of C. I mean, you could leave it as x. It doesn't matter. So yes to the first part. If so, find the point or points guaranteed by Rolle's theorem. So I'm going to find the derivative of f. And that's going to be sine of box, because it's chain rule. So derivative of sine of box is going to be cosine of box times the derivative of the box, but derivative of 2x is 2. And we want to know when it equals 0. So to solve this, I divide both sides by 2. So when is a cosine equal to 0? On a unit circle, you should know the cosine is 0 here and here. So pi over 2, 3 pi over 2, or negative pi over 2, negative 3 pi over 2, basically all the pi over 2's, and we're going from x is 0 to pi over 2. So what angles? So these are my angles. The cosine of what angles is 0? I claim plus or minus pi over 2, plus or minus 3 pi over 2, and on and on and on. Divide both sides by 2 to get rid of the 2 because we're solving for x. And we will end up with plus or minus pi over 4, plus or minus 3 pi over 4, plus or minus 5 pi over 4. But our domain is from 0 to pi over 2. So my answers must be between 0 and pi over 2. Therefore, I can ignore all the negatives because we can't have a negative. And which ones are between 0 and pi over 2? I claim there's only one of them here. That one. This is bigger than pi over 2. That's bigger than pi over 2. So our guaranteed value, we'll call it C, is pi over 4. And at that point, the derivative is 0. So that's example number 1. Checking if Rolle's theorem applies. That means all 3 conditions must be met. And then the guarantee of Rolle's theorem is that there's going to be a value of x where the derivative is 0. We solve for that value of x, and that is the guaranteed point. Okay, so that is Rolle's theorem. We are rolling on to mean value theorem. So mean value theorem is very similar to Rolle's theorem. I will read it to you and then explain. So we get the same conditions. It must be continuous on the closed interval. That's condition number 1. Continuous on a closed interval. I will label that number 1. Number 2, differentiable on an open interval. Now, this one only has 2 conditions, but the results are similar. There exists at least one point C. So there could be 1, but there could be more. And that point must be in between A and B. Cannot be equal to A and B. It's an open interval. Where? So here's where you're guaranteed. You're going to guarantee that if you take the average rate of change, that's going to equal the derivative at some point C at least one time. So I'm going to draw, well, I'm not going to draw, I have pictures below to give you a visual of what this means. You should know what the average rate of change is. What is f of b minus fa over b minus a? That is the average rate of change or the slope of the secant line. So I'm going to draw a secant line, kind of fat. Uh-oh, it didn't become a line. Let's try it again. There we go. So the slope of that line, let's look at it. This is a review of what we did early on. So we have a run and we have a rise. We call this point A, this is B, this would become f of A, this point would become f of B. So the distance from here to here would be f of B minus f of A. And the distance here to here would be B minus A. So if you want the slope of this line, it's rise over run, or f of B minus f of A over B minus A. That's kind of sloppy. Let me move that. You can't read that. So the slope of this line is rise over run. Here's a rise, here's a run. Look familiar? That's your famous formula for average rate of change. So the slope of the secant line is the average rate of change. So that is the slope of that blue line. Now, what are you guaranteed? You're guaranteed that the derivative at some point C will be equal to that. But what is the derivative? That is the slope of the tangent line, right? So here's what I'm going to do. I'm going to take this line, I'm going to copy and paste it. I think I'm going to copy and paste. Try it again. Copy and paste. It's not letting me do it. I don't know why. One more time. Third time's the charm. Ain't gonna happen. So I'm just gonna draw a parallel line to that and show you what's happening. There's a parallel line. So we're gonna take that line, and what it's saying is that there's gonna be a place where the derivative is equal to the slope of that line, but the derivative is the slope of the tangent line. Look, right there. There's my point. I found it. It's at that point where the slope of the secant line equals the slope of the tangent line, or in other words, where the average rate of change equals the derivative. So I claim I have found my C. There's my C. I claim that's C. So there's a value of x between A and B, where at that point, the derivative equals the slope of the secant line. Now, this has applications that I don't think you even realize right now, but there's serious applications of that. Now, this is just like Rolle's theorem. If you turn and rotate this graph to where the slope of this is 0, you will see the slope of that 0. So if you're finding the slope of this line, but that x values are the same, or excuse me, the y values, you'll get 0 here, and this will be 0, which becomes Rolle's theorem. So like I said, you don't have to know Rolle's theorem. Rolle's theorem is rolled up into the mean value theorem. Okay. Now, why does it say at least one point C? I'll give you an example with this one. We will draw the f of b minus f a or b minus a, the average rate of change, right there. There is the average rate of change. So I'm going to draw a line parallel to that. And we'll see where the slope of the tangent line is equal. It looks like right there, right? So I have found one point right there. That's going to be my C. We'll call that C2 because the other one's to the left. I'm going to draw, see if I can copy and paste. I don't know why it's not letting me. Nah, ain't going to happen. Let's do another one parallel. Okay, there's another point where that happens, right there. So there are 2 points. I'm going to call this one C2. No, C1. All right. So here's why it says there's at least one point C, meaning one or more. In this case, we can see there were 2 points where the slope of the tangent line equaled the slope of the secant line. So there you go. That is mean value theorem. Very powerful in application, and we're going to give you an example of that coming up shortly. So first example, we want to show that this meets the conditions of the mean value theorem. So condition 1 said that it must be, what was it? Continuous. Well, we know f of x is continuous. How do we know that? Because we know all polynomials are continuous. So we need to state that. Step 2, we need to state that f of x, and I want to say what interval that is, continuous from -2 to 2. And then f of x is differentiable on the interval from 2 to 2, open interval. And we know that the polynomial is differentiable everywhere. So the 2 conditions of mean value theorem are met. So then what's guaranteed? We're guaranteed that this, the average rate of change, must equal the derivative at some point C. I can do that. So I'm going to plug in 2. That's 16 minus 6, 10 plus 1 is 11. I'm going to plug in -2. That's -16 plus 9, -16 plus 9, negative 7, negative 6. I hope I'm doing this right. Over 4. Let me double check that. Plug in 2. That's 8. 16. 16 minus 6, 10 plus 1 is 11. I'm going to plug in negative 2. That's negative 8, negative 16. Negative 16, I plug in a negative 2, negative 16 plus, I'm doing negative, no, I'm doing positive. I am lost. What am I doing? I'm plugging in negative 2, right? So negative 2, that's negative 8, negative 16 plus 9, no, negative 16 plus 6. That's negative 10, negative 11. Wow. Am I that off? Do I need to do this a third time? Okay, let's plug it in. Negative 2. That's negative 8, negative 16. That's going to get us a plus 6. Negative 10 plus 1. That's negative 9. Wow. That's horrible. That must equal the derivative. So the derivative is going to be, let's do this to the side. F prime is 6x squared minus 3. So f prime c, you don't have to put the c in. I'm just doing it because that's the format they had. That's my variable. I could leave it as x and just solve for x, but 6c squared minus 3. This is 20 over 4. 20 over 4 is 5. Add 3 to both sides. Divide both sides by 6. So we get c squared is 4/3. We square root both sides. We get plus or minus square root of 4/3 is plus or minus 2 over radical 3. But let's look at our domain. Our domain is from negative 2 to 2. Well, I guess we have 2 points. So there are actually 2 points to satisfy that condition. Bam and bam. So there are actually 2 points in this case. We found both. So that is our example number 2. We'll keep on going to the next example. Example number 3. Okay, I want to check this answer to make sure I did it right. Okay, we are correct. Those are the 2 points. Okay, so we're good on example 2. Example 3 is from actually, I think it's a 2013 or 14 AP test. This was actually one of the questions from it. So I want to do this one. And I think this is the end of the lesson, not too long. Hot water is dripping through a coffee maker, filling a large cup with coffee. So if you want, I'm going to do a picture of a coffee maker. I don't know, lame-o picture. And you have things dripping, and you have a large cup underneath. So there's my beautiful coffee maker. And what do these things represent? Let's read this. The amount of coffee in the cup at any time is given by C. So C is the amount of coffee in the cup. It's important you understand what everything represents. Amount of coffee in cup. And T is in minutes. It's time in minutes. I should write that out. So T is time in the units of minutes. And the units of the coffee, they tell us somewhere it's ounces. Yes, ounces. So, ounces. Time in minutes. But let's read. From where? T is in minutes, so the time coffee's been dripping into the cup. Okay, so we're good at that. We have values. So here's what it says. After 0 seconds, there is no coffee in the cup. After 1 minute, not seconds, 1 minute, there's 5.3 ounces of coffee in a cup. After 2 minutes, there are 8.8. After 3 minutes, 11.2. You'll see at first it increases quickly. A lot of coffee in 1 minute. Not as much, and it's slowing down. And if you've ever seen coffee, it goes fast at first and then it slowly drips, not as fast all the way through the process. So that is what the idea is on this. We're trying to wrap our head around here. So part A is a very common question. We're trying to approximate that, okay? The derivative. We want to approximate C prime at 3.5. That's an instantaneous rate of change. That is the change in C over change in time at time t equals 3.5. That's another way of looking at it. How fast C is changing as t is changing? Well, we don't have the function C, so we can't take the derivative. So what do? We approximate. And so if we were to graph these points, we have 0, 0, 1, 5.3, 2, 8.8, 3, 11.2. I'm just making up stuff. It's not a perfect graph. And then 4, 12.8, 5, yeah, you get the idea, right? So you plot some points. And 1.5 is actually, so you have a guess the curve might look like this. And so you're trying to find the slope at 3.5 actually. 1, 2, 3, 4. So you're trying to find the slope of the tangent line at that point. But we don't have the function. So here's the concept. How do we approximate the instantaneous rate of change? We take an average rate of change. If we take the slope between those 2 points, the slope of that line mimics the slope of that'd be C prime, the slope of the tangent line. So conceptually, you need to see that. So this is the average rate of change. That's the instantaneous rate of change. And that's pretty darn close to that. So how do I approximate this? I do the average rate of change from 4 to 3. So I do C of 4 minus C of 3 over 4 minus 3. Well, C of 4, if we look at the chart, is 12.8 ounces. I guess OZ is ounces. I'd rather do that because I don't want to write it out. I don't know why OZ is ounces, but that's what it is. Minus 11.2 ounces over 4 minus 3. And then we get an approximate answer. What's that going to be? 1.6 over 1 ounces per minute. So that is our approximation for the derivative using the average rate of change. Here is the fun part, part B. Is there a time where the derivative equals 2? Now think about this. You don't have the function, so you can't set the function equal to 2. But here's the deal. If you look at mean value theorem, what does it do? It guarantees your derivative is going to equal some number. So the mean value theorem is what we're going to use. And we have to see if there's an application here. So we want to go between 2 and 4. So in this range, is there a time where the derivative is 2? Are we guaranteed that? Here's what we know. First, to apply mean value theorem, it must be differentiable and continuous. But look, it's differentiable. So we can say C is differentiable always. We just know that. If it's differentiable always, it's differentiable on our interval. So you could say on 2 to 4 if you wish. Now, here's the thing. You have to know, if something's differentiable, it must be continuous. That's part of the guarantee. That's part of the things you know. If it's differentiable, it must be continuous. Now, the converse doesn't work. If something's continuous, it doesn't mean it's differentiable because there could be a sharp point. So we should say, since C is differentiable, comma, therefore C is continuous. So now we have differentiability and continuity for this function. And I'm not going to say on, I'm going to say everywhere. C is differentiable everywhere. So I'm just going to say that. C is differentiable, given. Since C is differentiable, therefore C is continuous. We have differentiability and continuity. Now we're guaranteed what? By the mean value theorem, we are guaranteed that C prime at some point t will be equal to the average rate of change. We want it to equal what? 2. Is there a point either between those two or those two where the average rate of change is 2? Let's look at that. What's 11.2 minus 8.8? I don't know. That's 2.4. That's 2.4 over 1. That doesn't equal 2. Let's try these two. 12.8 minus 11.2, that's going to be 1.6 over 1. That doesn't equal 2. Let's do this point and that point. 12.8 minus 8.8 is 4 over 2. That is 2. So we're going to use 4 and 2. So here's our conclusion. It's going to be C of 4 minus C of 2 over 4 minus 2. That is a guarantee of the mean value theorem. If you have a differentiable continuous function, then there must be a place where the derivative equals the average rate of change. I don't know why. So C prime of t equals, so C of 4 is going to be 12.8 minus 8.8. 12.8 minus 8.8 over 2, which is 4 over 2, equals 2. So by the mean value theorem, we're guaranteed the derivative will equal 2. And that's what we're trying to prove. There must be a time where C prime of t equals 2. So I would say, therefore, this must be true. That's the conclusion, mean value theorem. That's the end of this lesson. Bye-bye.